All right, we're going to start off by doing number 55 from the homework last night. From which page? Oh, page 492.
Yeah.
Number 55 from page 492. So we have the function f of x is equal to f of x is equal to 3 sine x. And for part A, we're being asked to find the zeros of f on the interval negative 2 pi to 4 pi. So we're going to find all of the values of x that make 3 sine x equal 0. This thing doesn't start. And of course, that's going to happen just whenever sine x is equal to 0. And we know on that interval, sine x is 0 at 0, pi, and any multiple of pi. So between negative 2 pi and 4 pi, any multiple of pi, it's going to be 0. So negative 2 pi, negative pi, 0, pi, 2 pi, 3 pi, and 4 pi are going to be all the zeros that we have in that interval. If we want to go ahead and graph the function on that interval, right, it's going to have the only transformation it has is it has a amplitude of 3, so it's going to go up to positive 3 and down to negative 3. So you go pi, 2 pi, 3 pi, 4 pi, 1, 2 pi. So it starts at 0, hits its max, goes down, hits its min, hits its 0, max, down, min, 0. And then does a similar thing on this side. All right, so there's your function graphed. They want us to solve the equation, so that's part B. Solve the equation f of x equals 3/2. So when does 3 sine x equal 3/2? Well, that's when sine x equals 1/2, right? And sine x equals 1/2 at multiples of, and then graphically, what is this going to look like? You know, 3 sine x, or 3 sine x equaling 3/2. 3/2 is 1.5, meaning it's going to be right here, right? So all the intersection points with that line are the graphical representation. So we're going to have 1, 2, 3, 4, 5, 6 solutions to that equation over that interval, right, between 4 pi and negative 2 pi. Right, so sine x equals 1/2 at when it's in the first and second quadrant, because it has to be positive. So pi over 6 is one of them. And then 5 pi over 6 is the next one, right? And then going, so pi over 6, 5 pi over 6. Right? And then going over here, it's also going to happen at 2 pi plus pi over 6, which is going to be 13 pi over 6. And then 5 more than that, which would be 18 pi over, which would be 3 pi, so yeah, 17 pi over 6. Right, and then going into the negative here, it's going to be we're going to be looking at negative 7 pi over 6, as well as negative negative 11 pi over 6. So those are these two intersection points right here. So negative 7 pi over 6 and negative 11 pi over 6. All right, so those are the 6 solutions to that equation. So those points occur here, 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 here. So graphically, that's what's going on. Algebraically, that's how we solve it. Whereas f of x greater than 3/2, it's greater than 3/2 on this interval, and this interval. So I'll just do that up here. So part D, the intervals over which it's greater than that would be negative 11 pi over 6 to negative 7 pi over 6, union pi over 6 to 5 pi over 6, union 13 pi over 6 to 17 pi over 6. Right. Those are the 3 intervals over which it is greater than that line, which once again we can sort of identify that graphically, and as long as we know the intersection points, we can write out those intervals where it's greater than that. Okay, so that's 55 from the homework. Are there any other questions from the homework?
Can we do 13 on page 500?
For 13, and we're on page 500. 13 on page 500. For 13, we're trying to solve the equation sine squared theta is equal to 6 times cosine theta plus 1. All right, and so in this section here, we had been using, we've been using trig identities to solve these. So what we can do is sine squared theta. I'd probably use a trig identity for that one. Write that as 1 minus cosine squared theta. Right, and then distribute the 6. And now we have a quadratic trigonometric equation. So put the cosine squared theta over here plus 6 cosine theta, and then 6 minus 1 is 5. Right, equals 0. And so we want to go ahead and factor that now. And so it should be cosine theta, and then 1 and 5 are the only two factors of 5, and if they're both the same sign, they add up to 6 if they're both positive. Right, so cosine theta equals negative 1, or cosine theta equals negative 5. Now, and this is restricted to the interval 0, so theta, we want to find all the solutions between 0 and 2 pi. So cosine theta equals negative 1 on that interval. Where does theta equal, cosine theta equal negative 1? Well, that happens when theta is equal to pi, right? And is cosine theta ever equal to negative 5? So there's no solution to that equation. So the only solution that works is theta equals pi here. Okay? Any other questions? None? Okay. So, one more type of trigonometric equation before we move on to the next chapter, which we will do today and start talking about triangle trigonometry. But this type of trigonometric equation is called a linear trig equation. And linear trig equations involve sine and cosine both taken to the first power. So a basic example is sine theta plus cosine theta is equal to 1. Right, and so in this case, there isn't really a good trig. I mean, there are some identities that you could apply to this, of course, but there isn't an identity that you could apply to this that's really, like, right away, that's really going to help you out here. So in the case of linear trig equations, one trick to use is to go ahead and start off by squaring both sides of the equation. So just take both sides of the equation and square them, right? And we'll get sine squared theta this way plus 2 sine theta cosine theta plus cosine squared theta equals 1, right? Just squaring the binomial there. First, outer, inner, last. The outer and the inner terms combine to give me 2 sine theta cosine theta. Now there's some definite identities we can apply here. What's sine squared theta plus cosine squared theta? Equal to always 1. So we really have this, which means we just have 2 sine theta cosine theta equals 0, right? And now they're multiplied together, so we can apply the zero product property. The only way is sine theta times cosine theta. And I know you're going to look at this and say, well, that's sine double angle, right? But having sine 2 theta equals 0 doesn't really help us any more than this does, right? Because this is a factored trig equation now because we have sine theta times cosine theta. So the only way those, anytime we have a nice factored situation like this, we can just have them both equal to 0 by the zero product property, right? And sine theta equals 0 when theta equals what? On the interval, on the interval between, should specified, between 0 and 2 pi, where does sine theta equal 0? 0 and pi. Cosine theta, where does that equal 0? And? Okay, so the question is, do these actually, remember, anytime we square both sides of an equation, we have to be very careful that we haven't added any erroneous solutions. Because if you're multiplying both sides of an equation by anything that contains a variable, there's always a chance that you're adding an erroneous solution. So we got to go back and check all of our solutions. 0 and pi make perfect sense, right? Because sine of 0 is 0 and cosine of 0 is 1. So that makes them both work, right? Sine of pi, same deal. Sine of pi is 0, cosine of pi is, well, actually it doesn't work, does it? Because what's cosine of pi? That should be a quick and easy one, guys. Cosine pi, quadrantal angle. -1. Does -1 equal +1? No, so that one doesn't work. Pi over 2, right? Is that going to work? Well, pi over 2 makes what? That makes cosine 0 and sine 1. So that one works, right? What about 3 pi over 2, though? Cosine 3 pi over 2 is 0, so that's good. Sine of 3 pi over 2, though, is? So that doesn't work. So we have to make sure that we check. So the only two solutions that actually work are 0 and pi over 2. So just remember that anytime we are squaring both sides of an equation, we always have to be careful to check our answers at the end to make sure that we haven't added any erroneous answers that didn't actually exist in the original equation, which is always a possibility. Okay, so that's just, if you run into a linear trig equation, your strategy is to square both sides of the equation to try and solve it. All right, so we're done with chapter 7 now, and we're going to move into first of all, right triangle trigonometry and just solving triangles in general. So I like to group this all together and just call it triangle trigonometry. Anytime we're using trigonometry to help solve triangles. All right, we're going to start off and talk about right triangles really briefly. Honestly, though, I'm going to blow right through this as quickly as possible because I feel like you've had a lot of right triangle trigonometry. You have a general sense of how to use trigonometry to solve right triangles. You might need some review on that, but after that, we're going to get right into law of sines. We need to talk about things involving law of sines like the ambiguous case and so forth. So right triangles, just as a reminder really quickly, if we have a right triangle, right, we normally refer to the two legs as A and B, and the hypotenuse is always C, right? And so our alternate definition for the trig functions, and where they sort of came from originally, so instead of our unit circle definition, now we're going to sort of, if we're working with right triangles, we're going to revert to our right triangle definition of trig, which really they're the same thing, it turns out. It's just they're defined in different ways, but they're all based on the same principles. But when we're talking about right triangles, sine theta, right, that's going to be what? Opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. I'm sure I'm not telling you anything you didn't already know. Tan theta, opposite over adjacent. Cosecant theta, hypotenuse over opposite. Secant theta is hypotenuse over adjacent. And then cotangent theta is equal to adjacent over opposite, right? So we knew that. And the thing is, if you apply all of these definitions, if you go back to the unit circle and you apply all of these definitions to the reference triangles in the unit circle, you'll find that these definitions match up directly with the unit circle definitions, right? So they're really the same thing. This is just a different way of describing the same exact definitions that we used in the unit circle earlier. Right, because if you look at the unit circle, we'll look at it really quickly. So our normal definitions, right? Here's my unit circle, right? And here's my reference triangle in my unit circle. And so the point, the x and the y coordinates, the point that the terminal side crosses the unit circle right here, right? That is, well, we know our unit circle definition was that, let's just look at sine. And like this is theta, of course. That sine theta, by our unit circle definition, is just equal to the y-coordinate. But let's apply the right triangle definition to our reference triangle that creates in the unit circle. And well, we always know that hypotenuse is 1 here in the reference triangle. And so this side is x and this side is y. So sine theta by our right triangle definition would be y opposite over hypotenuse, which is equal to y. So we can see now that our unit circle definition and our right triangle definitions are really the same thing. They're just different ways of describing them. The unit circle definition is more suitable when you're just working with angles in the coordinate plane. You're not worried about triangles. The right triangle definitions, of course, we use when we're talking about right triangles or any other type of triangles usually. So they're the same, it's two different ways of describing the same concept, essentially. And so we can solve right triangles using trigonometry, as we know. So the big thing is there's going to be a lot of word problems, so we're just going to dive right into word problems here. Okay, and so this is the first example we'll look at. We're just going to write a basic trigonometric function using the trig formulas that we just introduced for right triangles here. So you want to write a function for this area right here, right? That's entirely in terms of theta. You're going to have to use trig ratios, triangle ratios, like the formulas that we just introduced to do that, right? And then once you have that function, you're going to go ahead and find where A is largest, maximize it using your calculator. So give that a shot. So we're going to start off by just writing an area formula that doesn't necessarily only involve theta, and then we'll get into it after there. So we have the area of the two triangles, right? Which then we're going to add that to the area of the square. Thus, the area of the two triangles is going to be 1/2 base times height. The base can be that, and the height can be A, right? Plus, right, the area of the square, which is going to be 4 times B, right? So the question is, how can we get B and A entirely in terms of theta, right, using trig functions? Well, if we look at that triangle there, we can see that B, if we're looking at theta there, and we'll look at this triangle at the bottom here, we'll use that as a reference, because that's the same triangle we have here and here. We see that sine theta is going to be equal to opposite over hypotenuse. And cosine theta is going to be equal to adjacent over hypotenuse, meaning that B is going to be equal to 4 sine theta, and A is going to be equal to 4 cosine theta. Right? So A, if we get it strictly in terms of theta, is going to be equal to 4 sine theta times 4 cosine theta all over 2 plus 4 times 4 sine theta. Right, and if we simplify that, we'll end up getting 4 sine theta cosine theta plus 16 sine theta. So that should be our A of theta, right? And if we go ahead and we maximize that in our calculator. So one mistake I made here is there's 2 triangles, so instead of being the area of having the area of the one triangle and having that be 1/2, it should be just regular, just B times A, and so that means we need to change this whole situation here. So we should actually, since there's 2 triangles, our total area of those triangles is times A times B, and so we should actually end up with, here we have 4 sine theta times 4 cosine theta, and we end up with 16 sine theta cosine theta there. And one thing we have to keep in mind when we are when we're looking here and we're trying to maximize this function A theta, we should think about the domain. What's the domain of the angle theta? What's the smallest theta can be, and have this make sense? What's the largest theta can be? What values is theta going to be between? Anyone? Can theta be negative? So what's the smallest value for theta? 0. What's the largest value that theta probably should be? Yeah, pi over 2. Well, I mean, we don't want it to, for the rain gutter to have this shape, we can't go past 90, right? If we rotate this over here, it's no longer in the same shape anymore. So we're probably going to stop at 90 there. So we're only looking to maximize this over that interval in this maximization problem here, and that's the last part. If we maximize A theta over this domain on our calculator, we're going to get that the max value for A is going to be 2.618 square inches. So there we go. So that's how we can use functions that involve right triangle trig ratios to help us solve problems like this. All right, so let's look at this another word problem involving right triangles here. So we have meteorologists. They find the height of a cloud using an instrument called a ceilometer. Ceilometer, it's a light projector that directs vertical light up to the cloud base, and a light detector that scans the cloud to detect the light beam. So we see that, the light detector is, in one area over here. The light projector is here that goes straight up. And so there's going to be an angle measured here. And so they're measuring the heights of the clouds at Midway Airport in Chicago. And the light projector was 300 feet from the light detector, right? And the light detector is pointed up at an angle of 75 degrees at the point in the cloud where the light projector hits the cloud, right? The question is, how high is the cloud cover? We'll have to use trigonometry to solve this problem. So if we take a look at this one right here, we just want to find the height of the cloud. We know the distance of the light detector from the light projector. We know the angle, and we call this the angle of elevation, by the way. That's a special term we use when we're dealing with situations like this. This is the, whoops, let's try that again. 75 degrees is the angle of elevation, right? And so we want to figure, we know what the base is, we want to know the height, right? And we have the angle. So we're going to use the trig ratio that involves all 3 of these things. So tangent 75 equals opposite over adjacent, right? So we get tan 75 is equal to opposite over adjacent, and therefore h is going to be equal to 300 tangent 75. So we get 300 times tan 75 gives us negative 126, 0.210 feet. Yeah, so that doesn't make sense because it's a negative value, and we should be getting positive values for a length. And the issue there is that I had it in radian mode, so that's an important lesson, that you should always have your calculator in the right mode. In this case, I should have had it in degree mode because we're doing everything in degrees. And so if I had done it in degree mode, we get a much more reasonable answer, which is 1,119.615 feet, which is a much more reasonable height for a cloud to be at, as opposed to having the cloud below the surface of the Earth, which wouldn't really make a lot of sense. So there's our answer right there. Okay, let's look at a couple more examples here. So, for instance, sometimes we have multiple triangles going on. All right. So we have a statue. This is a situation where we have a statue on top of a building. Right, it's a statue of Ceres, the Roman goddess of wheat, apparently. And so someone on the street is looking. We can take two separate observations. One from the street level all the way up to the base of the statue, and one from the street level up to the head of the statue, the top of the head of the statue. And so both these observations are taken 400 feet from the building, and it's found that we have to look up at a 55.1 degree angle to look at the base of the statue, and a 56.5 degree angle to look at the height of the statue. The question becomes, right, if those are the angles, and that's how far away we are, and the question is, how tall is the statue? Right, so we're going to have to use, and they even drew out the two, they took these over and drew the two triangles separately for us. They're both right triangles, of course. Using this information, how can we find the height of the statue? And it's, of course, once again going to involve right triangle trigonometry. So give that one a shot. Okay, so looking at this situation right here with the two triangles, what we can do is, if I know the height of the height to the base of the triangle, the height to the base of the statue, and I also know the height to the top of the statue, the difference between the two should be the actual height of the statue itself. So we're going to use tangent for this one as well. So tan of 55.1 degrees is going to be equal to b over 400. And tan of 56.5 degrees will be equal to b prime over 400, as they called it. And so b will be equal to 400 times tan of 55.1, and b prime will be equal to 400, well, not 4,000, but 400 times tan of 56.5. And so what we'll get, so from that we get that b is equal to 573.39 and b prime is 604.33. And if we go ahead and we subtract b from b prime, we'll get approximately 30.95 feet. Or almost 31 feet tall for the height of the statue. So definitely want to be able to use more than one of those measurements there. All right. A concept that involves right triangles that we want to talk about is bearing. Right, so if something is traveling on the planet, whether it's a plane or a train or a boat, its bearing is often important. And so the bearings go off the cardinal directions, right? And so we know that our four cardinal directions are north, south, east, and west. Right, so let's say that we have an object that's sort of traveling 30 degrees east of north. Well, the way that we're going to write that is north 30 degrees east. right? And so we always base our bearing off north and south. So the angle that that we make with north or south is the angle we're concerned with. So this angle, let's say there's an angle of 70 degrees right here. This is going to be, and this is farther, and so this is going to be north, sorry, because it's above the our x-axis here, north 70 degrees west, right? And so let's say that we have one that's, say this angle right here is 20 degrees, then what would this one be? How would I write that one? South, 20 degrees east. So 20 degrees east of south, that might also be called too. So it's the angle is always based off either north or south. So over here, this one, if this is 50 degrees, right, this would be south, 50 degrees west. Right, so it's important to be able to just know what that means, pretty much. Okay, so let's go ahead and look at a word problem example that actually involves bearing and how we can get right triangle trigonometry involved in that. So, for instance, if we have any aspiring pilots in the room here, this is a good one because this is something that pilots have to do when they're navigating all the time. So we have a Boeing 777 takes off from O'Hare on runway 2 left, which has a bearing of north 20 degrees east. That's the direction the runway is pointed and the direction that the plane is pointing when it takes off from the runway. After flying for 1 mile, the pilot of the aircraft requests permission to turn 9 degrees and head toward the northwest. The request is granted. After the plane goes 2 miles in this direction, what bearing should the control tower use to locate the aircraft? So what direction does the tower have to look in, right, to actually see the aircraft after it's gone 2 miles in its new direction? So the aircraft's traveled a total of 3 miles at that point. And so the key here is draw your cardinal directions, draw the airport at the center, right, and then sort of plot the path of the airplane, and you should have it create some triangles, which then you can hopefully measure the angle that the tower has to look to see the aircraft. All right, well, let's go ahead and take a look at this. I'll start off by drawing my compass directions, right? And we'll put the airport right at the center of our compass here. So we have north, south, east, and west. All right, so I forgot to hit record again, so I'm just going to talk you through it really quickly here. So we start off by drawing our cardinal directions here, north, south, east, west. The plane starts off heading in a direction 20 degrees east of north, right? So for the first mile, it heads in this direction, and then it does a full 9-degree turn, forming a 90-degree angle with its original bearing here, and starts heading off, which would, if we go 90 degrees, if we go a whole 9 degrees, that's going to end up being 70 degrees west of north now, right? So this angle right here with the vertical would be 70. This angle right here is 20, and then travels for another 2 miles in that direction. And now the question is, what is this direction that from the control tower I have to look out to see the plane, right? And so this direction right here, this distance forms a right triangle with the other two that we have. And so we want to know this angle right here essentially. And because they're going to be looking west of north, right? What degree west of north does the tower have to look to see the plane, right? So this forms a right triangle. And if I can find this bigger angle right here of the right triangle, I can then subtract 20 from it, and that should give me this angle right here. So I can set up my trigonometric ratio. Tan theta is going to be equal to opposite over adjacent, so tan theta equals 2 over 1. So theta will equal inverse tan of 2, right? And if I plug it into my calculator, I will get 63.435 degrees, right? So it's going to be 63.435 degrees. And what's the direction going to be, guys? How should I write that? Oh, I'm sorry. What do I have to do first? I'm actually not done. Yeah, my bearing, the bearing that we're going to be looking at is going to be 63.4. I'm going to round to 63.4 minus 20, which will give me 43.4 degrees, and that's going to be north, 43.4 west, right? So 43.4 degrees west of north is the direction, is the bearing that we're going to have to look in to see to see where the plane is right there. So this type of bearing problem is cool because it is very applicable, right, in terms of people actually do use this on a daily basis to do things like this when we're talking about planes and ships for that matter. All right, we have a little time left. All right, and a lot of you probably remember law of sines. We use law of sines when we have for general, what we call general triangles, triangles that aren't right triangles. Because all this stuff that we were using before in the right triangle section works great if we have a right triangle. But if we do not have a right triangle, then we are sort of out of luck, right? In terms of using trigonometry. We can't just use right triangle trig if we have a triangle that's not a right triangle. So the first question is, if we have a triangle that's not a right triangle, what information do we have about it, right? And so there's a bunch of different cases, right? What information do I know? And I need to, generally speaking, I need to know at least 3 things about the triangle. So in this case, let's assume that what I'm going to put in blue the information that we know and red the information that we don't. So in this triangle right here, all the things in blue we know and all the things in red we don't. So if I have an angle, a side, and an angle, and notice the side is between the 2 angles in this case, we call that ASA, right? If, on the other hand, I have a situation like this where I know a side, I know an angle, sorry, that should be in red, that last one. So in this case, I have an angle, and a side. We're going to call this AAS, angle, angle, side, right? And these should not only be familiar from last year in law of sines, but should also be familiar from geometry when you're talking about your congruence theorems. They also based everything off of the information configuration that you have about the triangle. The other one would be, right, whoops. Another one would be if we have the 2 sides and an angle. So, sorry, this jumped forward a little bit, but let me go back and explain it. So we have angle, side, angle, right? We have angle, angle, side. We have side, side, angle when we know 2 sides and an angle that's not between the 2. We have side, angle, side when the angle, we do know 2 sides, but the angle is between the 2. Then we have that. The angle is not between the 2. We have SSA. SSA, as we're going to see, can be problematic sometimes. And lastly, if we have all 3 sides, that's SSS. Law of sines we're going to use to solve angle, side, angle, angle, side, angle triangles and angle, angle, side triangles primarily. We can use them to solve SSA triangles, but we have to be careful about that because it turns out there's going to be some weird cases there. And law of sines doesn't work at all for SSS or SAS. For these 2, we're going to have to use law of cosines. But these are all the different configurations that we can have for general triangles in terms of the information that we have about them. And it's really important the order that we have it in. As we can see, SSA and SAS are very different, just like ASA and AAS are also very different. Even though they have the same type of information, it's not in the same order. All right, I already wrote it out here because we had once again, we had to jump forward here. So if we have our triangle here with sides A, B, and C and angles big A, I'll even write down here, big A, big B, and big C, right? Then law of sines, this is law of sines right here, involves sine, right? Says that sine of angle A over A equals sine of angle B over B, which equals sine of angle C over C, right? And I can pair up any 2 of these depending on what I need to do to solve the problem I'm looking at. And also, an unrelated but useful theorem that we should also be using is the angle sum theorem, which is that the interior angles of a triangle sum to 180. You should know that from geometry, of course. So, basic example of using law of sines would be the following, where we have a triangle right here where we have a 40-degree angle, a 60-degree angle. We know this angle has a length of side 4, but we don't know BC or angle C, right? And so in this case, what type of information would we have? What configuration is this? This is Angle, angle, side, right? That's the angle, angle, side configuration, so we can definitely use law of sines for that. So how can we set up a law of sines equation that would involve one of the three variables that we're trying to look for? Sine of 40 over 4 equals sine of 60 over b. So we can use this equation by setting up a law of sines equation there. We can solve for side b. So side b will be equal to 4 sine 60 over sine 40, right? 4 times sine 60 divided by sine 40, and we'll get 5.389, right? Angle C is really easy. Angle C is just going to be equal to what? How can we can find that without law of sines, right? We can just subtract 40 and 60 from 180, right? And that, what's left over has to be angle C. So angle C is 80 degrees. So we found one of the sides, we've found one of the angles. All we have to do is find the last side. Why don't we use law of sines to find the last side? Because the problem is we could use actually we can't use Pythagorean theorem, right? I almost made a huge mistake there. Remember, Pythagorean theorem only applies to right triangles, so resist the temptation to do b squared plus c squared equals a squared or whatever, or c squared equals a squared plus b squared, because it doesn't work here. So we have to use law of sines now that we have angle C to solve for side C as well. So we'll do sine of 40 over 4 will be equal to sine of 80 over C, and so C will equal 4 sine 80 over sine 40, right? If I go ahead and solve for C. And so C is going to be approximately equal to C will be approximately equal to 6.128, right? So we found side B, side C, and the unknown angle. So if you're asked to solve a triangle, right, that's what they're looking for. Just find all the unknown sides and angles. Okay, really quickly, just because it doesn't take that long, let's say that I have a triangle where I know that one of the angles maybe is 35 degrees, another angle is 15 degrees. Right, and I know side 5 right there. And I want to go ahead and solve this triangle right here. And then let's say this is side B, and this is side A, right, and this is angle C. Let's make that look a little more like a 15. Right, and this, what configuration is this right here? That's angle, side angle. And actually, I said before, I think I might have misspoken before and said we couldn't use law of sines to solve that, but we can, because right away I can find angle C, right? What's the measure of angle C? It's going to be 180 minus 15 minus 35, right? We can just use the angle sum theorem for that one. And we have 130 degrees. So right away we have angle C, and now I have an angle across from a side here. I know an angle across from a side which is necessary for law of sines. And I can go ahead and set up my equation. Sine of 130 over 5 is going to be equal to, let's just say sine of 15 over B. And so B is going to be equal to 5 sine 15 over sine 130. Right? And we get 1.689. And then I set up the other one. I can do sine 130 over 5 is equal to sine 35 over A. And so A will be equal to 5 sine 35 over sine 130. Right? And we'll get for A 3.744. Right, so those are the two scenarios that we want to know how now, if we have an ASA triangle or if we have an A. So your homework tonight's from 3 different sections because we're sort of cruising here. This first one is from the old handout from yesterday. And these 2 are going to be from the new handout that I will photocopy and send out to everyone today. All right, so like I said, we're going to finish up all of our trigonometry. I guess I haven't said it yet, but we're going to finish up all of our trigonometry tomorrow, and then next week I hope to devote entirely to sequences and series. And then at the end of the week, I'll let you know the things that you're still going to need to study to prepare yourself for the exam, which will be later in August, to give you some time to prep for the stuff that we won't have time to go over. Have a good day.